if you are just using this to change the dimensions, usually you can just multiply by a matrix. So you would multiply by a 512 by 1024 matrix to change the size. Another thing to keep in mind is if you expect this to be within a certain range, you would probably want the output to be within a certain range. So if this is after taking something like a tan h, which means your value should be between -1 and 1, you should probably also do a tan h before putting it into the decoder, just so it's within the same range that you would expect. You could have a multi-layer perceptron. You could have anything else. So.
You're good, by the way.
Yeah, OK, thanks. Yeah.
In a previous slide,
Uh-huh. Yep.
My question is that the input for the decoder is the ground truth or the previous layer previous?
Oh, that's a very good question. During training time, the most common thing to do is to input the ground truth. And this is a method called teacher forcing. Teacher forcing, the reason why it's called teacher forcing is you have a teacher that tells you the correct answer, and you're forcing the network to basically output this. But the problem with this is at test time, when you want to actually generate things, you make mistakes. And so you want to take, sometimes during training time, you want to take into account the mistakes. And there's a bunch of different ways to do this, like randomly sampling things, dropping out the previous word, reinforcement learning, search-based structured prediction. There's a whole list of methods to fix this problem, but I'm not going to be able to cover all of them here this time, I think. If you want references, I can give references at the end of the class. Any other questions? No? OK. So I'm actually going to touch on that a little bit here in terms of methods of generation from these models. So because the model itself is pretty simple, most of the complexity comes in when you actually want to generate things from the models. So now we have a model of P of y given x, P of our output given our input. So how do we generate a sentence? And there's basically two methods to do so. One is sampling. We try to generate a random sentence according to the distribution. And the other one is argmax. So we want to try to generate the sentence with the highest probability. So first, talking about sampling, in order to generate from these models, the simplest way to do so is with a method called ancestral sampling. So this basically is a method for generating variables by sampling one variable first, then sampling the next variable next, conditioned on the first variable. So our language models, or conditional language models, make this very easy for us because each time we can sample the first word in the sentence first, then the second word in the sentence, the third word in the sentence, and continue to go through until the end of the sentence. So the way this looks is a while loop. So until we reach the end of sentence symbol, we generate the next symbol conditioned on all the symbols that we previously generated. So the good thing about this, sorry, this should be P of y given x. But the good thing about this is an exact method for sampling. We can exactly sample from the probability distribution and get random outputs according to P of y given x. So the reason why I mentioned this is exact is we can compare this to when we do the argmax, when we want to get the highest probability sentence. So in this case, one way to try to get the highest probability sentence is to step through one by one and pick the highest probability word each time. And this is not exact, because while it's exactly picking the next highest word, or the word with the highest probability for the next time, this is, it's not exactly calculating the full sentence with the highest probability. So this results in it often generating the easiest words first, and it will also prefer multiple common words to one rare word. So let's say we have the example, is this good for the, OK. I live in. then we have something next. And for some reason, our model is really bad at picking where I live, conditioned on whatever information it has. So it has two options, or three options. It has New York, New Jersey, and Pittsburgh. And the probability of New York is 0.3. The probability of New Jersey is 0.3, or let's say 0.35, 0.25. And the probability of Pittsburgh is 0.4. So what happens in this case is basically, you see we have new twice. So the probability of new becomes 0.6. So then when we're comparing new and Pittsburgh, it picks new instead. And now it's stuck with having to pick New York, even though as a sentence that's less optimal than picking Pittsburgh. So this is just a very simple example, but this happens in real life as well. So greedy search will not get you the highest scoring sentence or highest scoring output in this case. On the other hand, if you're randomly sampling, if you want to test this out, you can see that actually randomly sampling according to this distribution, you'll get 0.6 half of the time, or you'll get new 0.6 of the time, Pittsburgh 0.4 of the time. Then you'll split the rest of the probability between these two. So you can, if you work it out, you can see that sampling would be exact. So instead of doing greedy search where you pick the one highest probability word, it's common to do something called beam search, where you maintain several paths. So for example, if we did beam search on this example and we set our beam size to 2, basically instead of taking just the one highest probability word, we would take the two highest probability words here. And that would still maintain Pittsburgh. And then as we continued searching, we would see that Pittsburgh was actually the better choice. So beam search is not exact unless you have an exponentially large beam, but it still helps a whole lot. And when you're creating sequence models, actually an incredibly small beam can still be very helpful, like 5 or 10 or something like this. So this is an important thing to know if you're actually making these models. This is something that you should be implementing. Do you have any questions about this stuff here? No. Does anyone have an idea when you would want to be sampling and when you would want to be doing kind of the argmax, like a beam search? Yeah.
Sampling seems more like a generative problem where like the application benefits from having multiple different results, where the argmax is like you're doing translation, you just want the best one.
So yeah, what would be an example of an application where you might want to sample things? So translation is a good example where you probably want to take an argmax.
Response generation.
Yeah, dialogue response generation. Image captioning. Yeah, image captioning is a little bit difficult. It's not clear whether you want more variety or you just want the best one. I guess it would depend on what your application is. But for example, if you have a dialogue system, there's a very strong argument that you would want actually to say something different every time. Because if every time you say hello and every time you get hello back, or every time you say how are you today and you get fine back, that might get a little bit boring. You might want some other options as well. Okay. Another reason why sampling is worth knowing is it does allow you to approximate the distribution of the outputs. So if for whatever reason you want to approximate the distribution of the outputs to estimate probabilities or whatever else, sampling is something that you can use. Okay. So now I'll move on to attention. And attention, as I said before, the encoder-decoder model is extremely simple. It's deceptively, you would never think this would work. And actually, the catch to it is that it doesn't actually work that well. And what actually works well is when you start introducing attention. So what is attention? Before going into that, I'm going to talk about a couple different ways you could represent a sentence or a sequence. There's a famous quote by Ray Mooney, who's a person who worked in semantics, that says, you can't cram the meaning of a whole bleeping sentence into a single bleeping vector. He said this at one of the first workshops on representation learning for NLP in 2014 when the encoder-decoder models had just come out and everybody was really excited about them. So what Ray Mooney was saying you can't do is take something like this as an example and turn it into a single vector and then expect this to contain all of the information, useful information in the sentence. But an alternative view is basically you take the sentence and you represent it as multiple vectors where each vector corresponds to one word. So I like to explain this in an intuitive way because I worked as a translator before. So when I worked as a translator, I would never have somebody give me a piece of text and say, please read this text, read this document. And then, OK, I'm going to take that text away from you. Now please translate it into Japanese or whatever. And what this is doing is it's basically saying this. It's saying, please read this text, memorize the whole thing, and output the entirety of the content accurately. So what attention is doing instead is it's saying, OK, please read the document, understand it, and then while you're translating the document, you can go back and read each of the words, the relevant words, at the appropriate time. And that's what translators actually do. They read the document, then they go back and they look at the words one by one as they're translating. So given that kind of intuition, what exactly are we doing? So we encode each word in the sentence into a vector. When we decode, we perform a linear combination of these vectors, and these are weighted by something called attention weights. And then we use this combination to pick the next word. So an example of this, a concrete example, basically we have the equivalent of I hate this movie in Japanese, and we've gotten up to I hate. So we want to calculate the probability of the next word. So we have the state, the RNN state here. We have vectors representing each of our words in the source sentence. And then based on this, we take a query vector. So this is basically the decoder state. And then we have a bunch of key vectors. These are basically the states for each word in the encoder. And based on this, for each query key pair, we calculate a weight or a score. And maybe that it's 2.1 for this one, minus 0.1 for this one, 0.3 minus 1.0. And this is a pairwise calculation. So I'll give some examples of this later. But basically, this is calculated only based on the query vector in each individual key vector. And then we normalize this to add up to 1 using a softmax. So this is saying, OK, for this one, we have 0.76, 0.13, 0.03, 0.08. And these all add up to 1. And then based on this, we have our attention scores, basically, or normalized attention scores. We take these value vectors, and we multiply each of them by this and take the weighted sum and turn this into a single vector. So what this is doing is it's basically saying, look at all the source, figure out which parts of the source were important. In this case, we assume that this part of the source is the most important because it has the highest weight. And then we use this to calculate the probability of the next word. So a graphical example of this is here. If you're doing translation from Japanese to English, when you generate the first English word, your attention weight basically is putting most of the weight on this particular word here. When you generate the second word, it's still focusing here. This happens to correspond to recommend. Then in the next words, it's focusing on this thing that is inexpensive, and then restaurant, etc. So this is the basic idea, and you can see that this is doing what I explained before, right? It's looking at each word in the source, and then when it generates the next word, it's focusing on particular ones that are best for generating things. Yeah.
I noticed it's very common in like attention visualizations that when you're generating like grammatical words that are unrelated to the input, it's the attention vectors doesn't change very often. I was wondering if there's like a reason for this.
When you're generating grammatical words that are not very related to the input, the attention vector doesn't change, or it can also be very broadly spread out, not focusing on any particular thing. And the reason why, that's a very good question. The reason why is, if you remember, in the encoder-decoder model, sorry, I have lots of slides, we have kind of two elements, right? We have this encoder, and we have the decoder. And what attention is doing is it's basically making the connection between the encoder and the decoder stronger. But when you generate grammatical words, there's actually no real connection between the encoder, like what's in the input and what's in the output, like you said. But the decoder still has an LSTM. The decoder is basically an LSTM language model, an RNN language model. So it doesn't even need to look at the input to know it has to generate a grammatical word there. So if you get, for example, I went, or no, let's see. It's hard to come up with a good example in English, because actually English, most of the grammatical words come before the before the word that you're thinking about. But oh, a period is a good example. So when you want to generate a period at the end of the sentence, you kind of know without even looking at the input that your sentence is basically done. So the period you can just generate without even looking at the input. And if that's the case, then this LSTM language model at the end generates it. And then attention doesn't really matter, right? You know, if it doesn't matter, it can just be random or completely flat or something like that. Does that make sense? Okay. Any other questions? So this, anything else? No? Okay. So this is really, really useful. Basically, any state-of-the-art model for machine translation or dialogue response generation, or maybe less for dialogue response generation, but machine translation, image captioning, et cetera, is going to be using attention in some way. So then the question is, how exactly do we calculate this? What are the methods that we do to take our query vector and our key vector and turn them into scores? There's actually a bunch of different ways to do this. So if Q is the query and K is the key, basically we want some way to say whether these correspond to each other well. One way is using a multi-layer perceptron. So as you know from this class, I'm sure multi-layer perceptrons can model anything. So this is a good first way to start modeling your attention. So you take the query vector and the key vector, you concatenate them together, you multiply them by a weight matrix to get some hidden, nodes. Then you multiply this by a vector, and this gives you a scalar corresponding to the score. So yeah, just to be completely clear. This is what's inside this gear right here. You assume you have a multi-layer perceptron inside the gear. This is flexible, and it's often very good with large data. The problem with this, though, is it's kind of an indirect way of modeling the similar. Oh, sorry, go ahead. Why do you use an activation function here? So, why use 10H? You can use any one you want. It's just an example. Yeah. Yeah. Any other questions? So this is a reasonably good way of a consistent space of word embeddings, where if you do linear transformations, or where you do a linear like movement in the space, or you do a transformation with a weight matrix, things tend to remain, kind of consistent, I guess. So the idea behind this bilinear function is basically, we assume that both of these are in a consistent space. We do a linear transformation between the query space and the key space. And then things that are close together, in other words, things that have a similar dot product after this transformation, are the ones that we want to be focusing on. Yeah?
Why does the NLP work well with large data? Why is that part of it?
So the reason why this would, let's see. The reason why this would work better with large data is because I think you've heard about how multi-layer perceptrons are universal function approximators. They can approximate any function, right? Are you familiar with the idea of bias and variance in machine learning? I can explain briefly. So basically, bias is specifically designing a model. When you specifically design a model to try to do the thing that you want, assuming your assumptions are correct, you'll do better. You'll be able to learn with smaller data. But the problem is all models are incorrect. So if you specifically design your model based on your assumptions, then you're going to fail at some point. Variance, on the other hand, is basically overfitting. It's not exactly overfitting, but that's a close enough approximation. And so if you design a model with very few assumptions, it's likely to pick up on kind of trivial variances or trivial changes in the data, and it will fail to generalize. So the multi-layer perceptron has very low bias because you're using a thing that can model anything, but it has high variance because it will be more likely to overfit. On the other hand, the bilinear thing, as I said, has very strong assumptions about the space of word embeddings, et cetera. But maybe this is not true. Maybe the linear transformation in the space doesn't hold across languages. And you can think of examples where it wouldn't, like words that are the same word in one language, but expressed in two different words in other languages. So the idea is basically, if you have lots and lots of data, you can learn this well. And because it can learn anything, it will work. This has a stronger assumption that works out a lot of the time, but will fail to scale at some points. So, yeah. And this is really important when designing neural models in general, I guess. So if you add more assumptions into your model, it will generalize better, but you might also be hobbling it in some ways. Yeah. Yeah. Yep. Yeah, these are all learned. Yeah. Anything else? Yeah. How do you choose this? 128, always 128. No, just kidding. It's a hyperparameter that you need to tune. So like everything in neural nets, the size of this is a hyperparameter. You can kind of come up with some rules of thumb, like the same size as your hidden layers. So if your hidden layers are 512, then you also want this to be 512. Or maybe it's 4 times smaller than your hidden layers, which seems to work pretty well a lot of the time. But like everything else, it's just something you need to tune. From a practical perspective, I would suggest taking a good, if you want to use these, I would suggest looking at a good sequence-to-sequence modeling toolkit, like OpenNMT or we make one called XNMT, and see what their defaults are. And usually they thought about their defaults, or read papers and see which ones they used. So, yeah. Yeah, that's the unfortunate thing about neural nets. You can't really, there's very few things you can say definitively. Any other questions? OK. So there's also some other attention score functions that you should be aware of. Another one is dot product. So this is taking the idea of this to the extreme. This is saying the key and the query vectors need to be in the same space, like exactly the same space. So you just take the dot product between these two and use that as your score function. So This is basically saying that if you have your English vectors and then you have, sorry, I speak Japanese, so all my examples are Japanese. But you have your Japanese vectors, then they should be in this in entirely the same space. So this is a very restrictive assumption, obviously. Whoops, I pressed something. So this is a very restrictive assumption, obviously, but when you don't have very much data, it actually ends up working, or even when you have lots of data, it ends up working relatively well. Another thing is that the key and the query vector, their sizes have to be the same. So if you want to use different sizes for your encoder and decoder, you can't use this. Oops. Thanks. Okay. Another one that's useful and just came out is the scaled dot product. So basically the idea here is as you increase the number of dimensions in your query and key vectors, the dot product will tend to be larger, assuming all other things are equal, assuming equal sizes. So what they do is they basically scale this by the size of the vectors. So they divide the score by square root of k. I'm not entirely sure where the square root came from. They didn't explain it, but it seems to work. Mm-hmm.
I think it's just the length of the unit vector. Oh wait, it's the square root of the magnitude. Never mind.
No, it's the square root of the dimensions. So yeah, it's the length of the unit vector. I would have thought that you would do like square root k times square root q, but maybe I'm wrong there. Yeah, there's probably some explanation there, but I wasn't able to figure it out exactly. Okay, so this is kind of the overview of attention, and yeah.
Could you talk a little about how you choose a score function, or you see for score function?
Sure. So I would never choose this one over this one. I think this one fixes a problem in the dot product. The scaled dot product fixes a problem in the dot product and will probably always be better, I guess. Then the question becomes, when do you want the scaled dot product? When do you want the bilinear function? When do you want the multi-layer perceptron? And my general impression is that you would want to, if you have more data, you'll want to use the one that's closer to the top. So if you have lots of data, the multi-layer perceptron might be better. If you have a moderate amount of data, the bilinear function would be better. And then if you don't have very much data at all, just a dot product would be better. That being said, it's not quite that simple. So, like most other things, when you incorporate some sort of bias into your model, it will tend to work better on smaller data, and it might work better on larger data also, because we never have enough data. So, yeah. Oh, that's a good question. With respect to this, I don't know. You'd have to do experiments to say the answer to that. But for sequence-to-sequence models or for machine translation models, I'd say maybe more than 1 billion words is pretty big. And then, yeah, so 1 billion words is like 50 million sentences. So that's pretty big. Then once you start getting down to less than 1 million, you start having to really work hard to get your models to work well. If you have more than 1 million sentences and you're on a relatively fixed domain, then things will work pretty well, I guess, for machine translation with neural MT. Then if, of course you can do things with less. And it's interesting to do things with less, but yeah. You have a question? No? Oh, sorry. Okay. Any other questions? Okay. So I'm going to talk a little bit about what we attend to next. So as I said, encoder-decoder models are very, very flexible. They can do lots of different things. I'm just going to give a couple examples of things that people have used these models for, and also talk specifically about how they engineered the models to fit these applications. So you might not be interested in any of the applications here. So if you're not interested in the applications, maybe you can get the intuition about like how you engineer a model to a new application that you actually are interested in. So the first thing you attend to, obviously, is an input sentence. So you have an input sentence. You want to generate an output sentence. There's more direct ways to attend to the input sentence, and these are really, really useful in many applications. The most common one is some sort of copy mechanism. So the idea of a copy mechanism is for example, translation, but especially things, it's also useful in translation, but it's especially useful in things like summarization, where in summarization we have, I am giving, or Graham Newbig is giving a lecture, Graham Newbig is giving a lecture on sequence-to-sequence models in CS 11785, was it? Deep learning. And you could shorten that to Graham is lecturing on sequence-to-sequence models in 11785 or something like that. So you're basically, the output is very directly connected to the input on a word-by-word level. And there are some changes, like I said giving a lecture, and that turned into lecturing, which is not a word-by-word copy. But in many of the cases, you do want to copy words. So what this does, basically, is it has a, it takes the input here, and then every time it generates a word, it can either generate the word just completely from the vocabulary, or it can generate the word by picking a word from the input sentence and using that to generate the output, or to directly copy that word into the output. So because this is a little bit small, just to write it down here, we have alpha, which is the probability of y given x, et cetera. And this is just our regular attention sequence model. And then we have 1 minus alpha, where we generate copy.